You are swimming in it right now. Every second of your life you move through it. You age because of it. You fall because of it. And yet, if someone asked you what it actually is, you would have no idea. Welcome to Spacetime, the single most important idea in all of physics. The invisible stage on which every event in the universe takes place. Albert Einstein gave us this concept over 100 years ago. It changed everything we thought we knew about reality. But here is the strange truth. We still do not understand it. Not really. We can measure it. We can bend it. We can watch it ripple across the cosmos. But ask a physicist what space-time actually is, and they will pause. They will think. And then they will admit that nobody knows. If you are excited to explore this mystery with us, take a second to hit that like button and subscribe to the channel. It really helps us bring you more content like this. Now, most videos about space-time show you the same picture. A stretched rubber sheet, a bowling ball sitting in the middle, planets rolling around it like marbles. And while that image is helpful, it only scratches the surface. The real story is far stranger. Space-time is not just curved. It expands. It can tear. It might even be made of tiny, invisible pieces too small to see. In this video, we are going to go beyond the trampoline. We are going to explore the 3 greatest breakthroughs that revealed what space-time can do. And we are going to face the 3 biggest mysteries that still haunt physics today: dark energy, quantum gravity, and the terrifying place where space-time itself breaks down. The singularity at the heart of a black hole. By the end, you will understand why Einstein's greatest idea is also his most mysterious, and why the search to understand space-time might be the most important quest in all of science. To understand space-time, we need to start with a world before Einstein. A world where space and time were 2 completely different things. Picture yourself in the year 1900. If you asked a scientist about space, they would describe it as a giant empty box. A stage where objects exist. It had 3 dimensions: length, width, and height. You could measure it with rulers. You could map it with coordinates. It was fixed, absolute, and the same for everyone. Time was different. Time was like a river flowing forward. It ticked away at the same rate everywhere in the universe. A second in London was the same as a second on Mars, the same as a second in a distant galaxy. Space told you where things were. Time told you when things happened. And that was that. Simple, clean, easy to understand. This picture of reality came from Isaac Newton, the greatest scientist who ever lived, at least until Einstein came along. Newton gave us the laws of motion. He explained gravity as a force that pulls objects together. An apple falls from a tree because Earth pulls it down. The moon orbits Earth because Earth pulls it in a circle. The math worked perfectly. For over 200 years, Newton's physics predicted everything we could see. But there was a problem hiding in plain sight. Newton's gravity worked instantly. If the sun suddenly vanished, Earth would immediately fly off into space. The gravitational effect would travel infinitely fast. But nothing can travel infinitely fast. And deep down, Newton knew something was off. He called gravity action at a distance and admitted he had no idea how it actually worked. He just knew that it did. Enter Albert Einstein, a young patent clerk in Switzerland with wild hair and even wilder ideas. In 1905, Einstein published a paper that would begin to unravel Newton's universe. It was called Special Relativity, and it started with a simple question. What would happen if you could ride alongside a beam of light? This was not just a thought experiment. Scientists had been studying light for decades, and they had discovered something very strange. No matter how fast you moved, light always traveled at the same speed. Imagine you are on a train moving at half the speed of light. You shine a flashlight forward. You might expect the light to travel at 1.5 times its normal speed, your speed plus the light's speed. But it does not. The light still travels at exactly the same speed it always does. This made no sense, unless something else was changing. Einstein realized that the something else was space and time themselves. If the speed of light is always constant, then space and time must be flexible. They must stretch and squeeze to keep light moving at the same rate for every observer. This leads to two mind-bending effects. The first is called time dilation. When you move very fast, time slows down for you. Not in some poetic sense. Literally. Your clock ticks slower, your heart beats slower, you age slower. If you flew away from Earth at nearly the speed of light and came back a year later by your watch, decades might have passed on Earth. This is not science fiction. We have tested it with atomic clocks on airplanes. The clocks that flew came back showing less time had passed than the clocks that stayed on the ground. The effect is tiny at airplane speeds, but it is real. And at speeds close to light, it becomes dramatic. The second effect is called length contraction. When you move very fast, space itself shrinks in the direction you are traveling. A spaceship flying past you at near light speed would look squished, flattened like a pancake. To the people inside, the ship, everything would look normal. But from your perspective, their space has compressed. This is not an optical illusion. It is not about how things look. It is about how space actually behaves when you move through it at extreme speeds. Taken together, time dilation and length contraction prove something revolutionary. Space and time are not separate things. They are connected. They trade off against each other. When you move through space faster, you move through time slower. They are two sides of the same coin, two parts of a single unified fabric. This fabric is what we call spacetime. A mathematician named Hermann Minkowski took Einstein's ideas and gave them a beautiful geometric form. Minkowski had actually been one of Einstein's teachers, and at first he was not impressed with his former student's work. But as he studied special relativity more closely, he realized something profound. He could describe all of Einstein's effects using geometry. 4-dimensional geometry. In Minkowski's picture, the universe is not a 3-dimensional stage where time passes. It is a 4-dimensional block where everything that ever happened and everything that ever will happen exists all at once. The past is not gone. The future is not yet to come. They are both out there, like different locations in space. We just happen to be experiencing one slice of this block at a time. This is called the block universe, and it is one of the most disturbing implications of Einstein's theory. It suggests that time does not flow. It suggests that the present moment is not special. Every moment is equally real. Your birth, your death, the dinosaurs, the heat, death of the universe. All of it exists together in the eternal 4-dimensional block of space-time. Now, you might be wondering what any of this has to do with gravity. So far, we have talked about space and time being connected. We have talked about things moving at constant speeds in straight lines. But special relativity does not include gravity. It does not explain why apples fall or why planets orbit. For that, we need Einstein's next breakthrough, General Relativity. And this is where things get really strange. Einstein spent 10 years working on General Relativity. It nearly broke him. But in 1915, he finally cracked it. And the key was a deceptively simple idea. gravity and acceleration feel exactly the same. Think about it this way. Imagine you are in an elevator with no windows. The elevator is sitting on the ground floor. You feel your normal weight. Your feet press against the floor. Now imagine the elevator is in deep space, far from any planet or star. But a rocket is attached to the bottom, accelerating upward at exactly the right rate. You would feel exactly the same. Your feet would press against the floor with the same force. There would be no experiment you could do to tell the difference. Einstein called this the equivalence principle. Gravity and acceleration are not just similar. They are identical. They are the same thing experienced from different perspectives. But wait, if you are accelerating in space, you are not moving in a straight line. Your path is curved. And Einstein realized that gravity must work the same way. Objects in a gravitational field are not being pulled by a force. They are following the natural curves of spacetime itself. Spacetime tells matter how to move. Matter tells spacetime how to curve. This is the core of general relativity, the most elegant equation in all of physics. Mass and energy create dips and curves in the fabric of spacetime, and objects simply follow those curves. The moon is not being pulled toward Earth by an invisible force. The moon is traveling in a straight line through curved spacetime, and that straight line happens to loop around Earth. We call it an orbit, but from the moon's perspective, it is not turning at all. It is going straight. The space itself is bent. This might sound crazy, but we have proof. Lots of proof. The first proof came from the planet Mercury. Mercury is the closest planet to the Sun. It feels the Sun's gravity more strongly than any other planet. And for centuries, astronomers had noticed something strange about Mercury's orbit. It was not quite right. Mercury's orbit is an ellipse, an oval shape, and the point of the ellipse closest to the Sun slowly rotates over time. This is called precession. Newton's gravity predicted some of this precession. Other planets tug on Mercury and shift its orbit, but the prediction was slightly off. Mercury's orbit precessed just a little bit more than Newton's laws could explain. For decades, no one knew why. Some scientists even proposed a hidden planet closer to the Sun that no one had ever seen. Einstein's general relativity explained the difference perfectly. The extra precession comes from the curvature of spacetime near the Sun. Mercury is so close that it feels the warping of space and time. And this warping adds a tiny extra twist to its orbit. When Einstein calculated this effect and found that it matched the observations exactly, he was so excited that he had heart palpitations. He knew he was onto something real. The second proof came from light itself. If spacetime is curved, then light should follow those curves. Light travels in straight lines, but a straight line through curved space is itself curved. This means that light passing near a massive object should bend. During a solar eclipse in 1919, astronomers tested this prediction. They photographed stars near the edge of the Sun, stars that would normally be hidden behind the Sun's glare. The eclipse blocked the Sun's light and made these stars visible. And sure enough, the stars appeared to be in slightly different positions than they should have been. The Sun's mass had bent the light from those stars, curved it around like a lens. This effect is called gravitational lensing, and it was headline news around the world. Einstein became an instant celebrity. Space-time was real. Today we see gravitational lensing everywhere we look in the cosmos. Massive galaxies bend the light from more distant galaxies behind them. Sometimes this bending creates multiple images of the same object. Sometimes it stretches a galaxy into a long arc or a ring. We call these Einstein rings. They are among the most beautiful objects in astronomy, and they are direct visual proof that space-time is curved by mass. But general relativity predicts more than just curved space. It also predicts curved time. Time passes slower in a gravitational field. The stronger the gravity, the slower time flows. This is called gravitational time dilation. And like the time dilation from special relativity, it is very real. GPS satellites have to account for it. These satellites orbit high above Earth, where gravity is weaker. Time passes slightly faster up there than it does on the surface. If we did not correct for this difference, GPS would drift by kilometers every day. It would be useless. The fact that your phone can tell you exactly where you are is proof that Einstein was right about time. Gravitational time dilation becomes extreme near very massive objects. Near a neutron star, time slows noticeably. Near a black hole, time nearly stops. If you fell toward a black hole, an outside observer would see you slow down and freeze at the edge. From your perspective, you would fall straight through. But the outside universe would seem to speed up around you. Stars would be born and die in what feels like moments. This is the bizarre reality of curved space-time. Speaking of black holes, this is where space-time starts to get truly terrifying. Black holes are predictions of general relativity. Einstein himself did not like them. He thought they were too strange to be real. But the math was clear. And today, we know black holes are everywhere. Every large galaxy has a supermassive black hole at its center. Smaller black holes are scattered throughout space. They form when massive stars die. When a star much bigger than our sun runs out of fuel, it collapses. The outer layers explode outward in a supernova, but the core falls inward. And if the core is massive enough, nothing can stop it. It keeps collapsing forever. The boundary of a black hole is called the event horizon. This is not a physical surface. You would not feel anything special as you crossed it, but it is a point of no return. Once you pass the event horizon, nothing can escape. Not matter, not light, not information. Space-time curves so severely that every direction leads inward. The future itself points toward the center. This is hard to wrap your head around. In normal space, you can move in any direction. Up, down, left, right, forward, back. But inside a black hole, the only direction is down, toward the singularity, toward the center. It is not that something is pulling you. It is that space-time has become so warped that all paths lead to the same place. And what happens at the center? This is where physics breaks down. General relativity predicts that all the mass of the black hole is crushed into a single point. Zero size, infinite density. This point is called a singularity, and it is a place where our equations give nonsense answers. Infinity is not a real physical quantity. It is a sign that something is wrong, that our theory has reached its limit. The singularity is not a real prediction about nature. It is a cry for help from the mathematics. General relativity is telling us that it does not work here. We need something better. This is the first great crisis of space-time, and we will return to it later. But for now, just know that black holes contain places where space-time itself falls apart. Let us pull back from black holes and look at the universe as a whole. Because space-time is not just curved in places, it is expanding everywhere. In the 1920s, an astronomer named Edwin Hubble made an astonishing discovery. He was studying distant galaxies, and he noticed that almost all of them were moving away from us. The farther away a galaxy was, the faster it was receding. This was not because galaxies are flying through space away from some central point. There is no central point. Instead, Space itself is stretching. The fabric of space-time is expanding. Imagine dots drawn on a balloon. As you inflate the balloon, every dot moves away from every other dot. No dot is at the center. The surface itself is growing. That is what the universe is doing. Space-time is inflating like the surface of a balloon. This discovery led to the Big Bang theory. If the universe is expanding now, it must have been smaller in the past. Run the clock backward far enough, and everything was compressed into an incredibly hot, dense state. That initial moment, about 13.8 billion years ago, was the beginning of space-time itself. There was no before the Big Bang, because time itself began at that moment. Space began at that moment. The question, what happened before the Big Bang, is like asking what is north of the North Pole. The question does not make sense. And just like the singularity inside a black hole, the Big Bang is a point where general relativity breaks down. The math gives infinite answers. We need a new theory to understand the true origin of space-time. For decades after Hubble's discovery, cosmologists assumed the expansion was slowing down. Gravity pulls matter together. So the expansion should be like a ball thrown into the air. It starts fast and gradually slows. Eventually, it might stop and reverse. The universe might collapse back into a big crunch. Or it might expand forever at a slower and slower rate. In the 1990s, two teams of astronomers set out to measure exactly how much the expansion was slowing. They studied distant supernovae. These are exploding stars with a very consistent brightness. By measuring how bright they appeared and how fast they were moving away, the astronomers could calculate how the expansion rate has changed over time. What they found shocked everyone. The expansion is not slowing down. It is speeding up. The universe is accelerating. This was so unexpected that the scientists checked their data over and over. They looked for errors. They found none. The universe is being pushed apart by something that acts like anti-gravity, something that fills empty space and pushes it to expand faster and faster. We call this something dark energy, and it is the second great crisis of space-time. Dark energy makes up about 68% of everything in the universe, yet we have almost no idea what it is. The simplest explanation is that empty space is not really empty. The vacuum itself has energy. Einstein actually predicted this possibility decades ago. He added a term to his equations called the cosmological constant, a value that represents the energy of empty space. At first, Einstein thought this was a mistake. He called it his biggest blunder. But now it seems he was right all along. The vacuum has energy. And this vacuum energy pushes space apart. But here is the problem. When physicists try to calculate how much energy the vacuum should have, they get a number that is wildly, absurdly wrong. The prediction is off by a factor of 10 to the 120th power. That is a 1 followed by 120 zeros. This is often called the worst prediction in the history of physics. Clearly, we are missing something huge, some deep principle about space-time that we do not yet understand. Dark energy is real. We can see its effects, but explaining it might require a complete revolution in physics. So we have two crises now. Singularities inside black holes, where space-time curves infinitely, and dark energy, where empty space-time somehow has energy that pushes the universe apart. Both of these point to gaps in our understanding. Both of these suggest that general relativity, as beautiful as it is incomplete. To make progress, we need to look at the other great pillar of modern physics, quantum mechanics. And this is where things get really weird. Quantum mechanics was developed in the early 20th century alongside relativity. But while Einstein was working on the nature of space and time, other physicists were exploring the nature of matter and energy at the smallest scales. And what they found was bizarre. At the quantum level, particles do not behave like tiny billiard balls. They behave like waves of probability. An electron does not have a definite position until you measure it. Before measurement, it exists in a blur of possibilities. It is everywhere and nowhere at once. This is not a limit of our knowledge. It is a fundamental feature of reality. The universe is genuinely uncertain at small scales. Quantum mechanics also tells us that you cannot know everything about a particle at once. If you measure its position precisely, you cannot know its momentum. If you know its momentum, you cannot pin down its position. This is Heisenberg's uncertainty principle. And it is not about measurement error. It is about the nature of existence. Particles do not have definite properties until they are observed. Reality is fuzzy and probabilistic at the quantum level. Another strange feature of quantum mechanics is that everything comes in discrete chunks. Energy is not continuous. It comes in packets called quanta. Light is made of individual photons. Matter is made of individual atoms and particles. There are no smooth transitions. Everything jumps from one quantum state to another. This granularity is built into the fabric of reality at the smallest scales. Now here is the problem. General relativity and quantum mechanics are both incredibly successful theories. General relativity explains gravity and the large-scale structure of the cosmos. It predicts black holes, gravitational waves, the expansion of the universe. Quantum mechanics explains atoms, molecules, chemistry, electronics. Every piece of technology you use relies on quantum physics. But these two theories speak different languages. General relativity describes a smooth, continuous fabric of spacetime that curves and stretches. Quantum mechanics describes a jumpy, probabilistic world of discrete particles and uncertain measurements. When you try to combine them, the math breaks down. This is most obvious at singularities. Inside a black hole, gravity becomes infinitely strong. To understand what happens at the singularity, you need both theories. You need general relativity because gravity is the dominant force. And you need quantum mechanics because everything is compressed to incredibly small scales. But when you try to use both theories together, you get nonsense. Infinite answers, equations that blow up. This failure is telling us something important. One or both of our theories is incomplete. We need a new theory, a theory of quantum gravity that combines the smooth curves of space-time with the discrete jumps of quantum mechanics. Finding this theory is one of the biggest challenges in physics. Some of the smartest people in the world have spent decades working on it. And while we do not have a complete answer yet, there are some promising ideas. Two of the most famous are loop quantum gravity and string theory. Each takes a different approach to the problem, and each suggests something surprising about the nature of space-time. Loop quantum gravity starts with a radical idea. What if space-time is not continuous? What if, at the smallest scales, space-time is made of tiny, discrete pieces? Think about a piece of cloth. From far away, it looks smooth and continuous. But zoom in close enough, and you see individual threads woven together. Loop quantum gravity suggests that space-time works the same way. At scales far smaller than an atom, smaller than a proton, smaller even than anything we can currently measure, space-time might be made of tiny loops. Knots of quantum information that weave together to create the fabric we experience. In this picture, there is the smallest possible length. You cannot divide space infinitely. there is a bottom level, a resolution limit to reality itself. This smallest length is called the Planck length. It is unimaginably tiny, about 10 to the negative 35th meters. A proton is about 100 billion times larger than the Planck length. We have no technology that can probe distances anywhere near this small. But loop quantum gravity says this is where spacetime becomes grainy, where the smooth curves of general relativity give way to quantum jumps and discrete structures. If spacetime has the smallest size, then singularities might not exist. A black hole cannot crush matter to a single point if points do not exist. The Planck length sets a flaw. Matter inside a black hole might be compressed to Planck scale density. Unimaginably dense, but not infinitely so. The singularity problem might be solved by the granular nature of quantum spacetime. Similarly, the Big Bang might not have been a true singularity. The universe might have started at Planck scale density, or perhaps it bounced from a previous collapsing universe. Loop quantum cosmology, an extension of loop quantum gravity, explores these possibilities. String theory takes a completely different approach. Instead of starting with space and time and trying to quantize them, string theory starts with quantum mechanics and derives space-time from something more fundamental. In string theory, the basic building blocks of nature are not point particles. They are tiny vibrating strings. These strings are incredibly small, about the Planck length, and the different ways they can vibrate correspond to different particles. One vibration pattern gives you an electron, another gives you a quark, another gives you a photon. But here is the strange part. For the math of string theory to work, there must be extra dimensions of space, not just the 3 we see. 10 dimensions, or in some versions, 11. Where are these extra dimensions? String theorists say they are curled up, compactified, rolled into tiny loops or complex shapes that are too small to detect. Each point in the space we see is actually a tiny 6 or 7 dimensional shape. We cannot see these shapes because they are far smaller than anything we can measure. In string theory, space-time is not fundamental. It emerges from something deeper. The strings and their interactions give rise to the appearance of space and time. This is called emergent space-time. It suggests that space and time might be like temperature or pressure, real, measurable quantities, but not the deepest level of description. Just as temperature emerges from the random motions of many particles, space-time might emerge from the quantum dance of strings. String theory also includes gravity naturally. One of the vibration patterns of a string corresponds to the graviton, the particle that carries the gravitational force. This is exciting because it means string theory automatically combines quantum mechanics and gravity. It might be the theory of quantum gravity we are looking for. But there are problems. String theory makes very few testable predictions. The extra dimensions are too small to see. The strings themselves are far beyond our experimental reach. And there are actually many different versions of string theory, a huge landscape of possibilities. Critics argue that string theory is more mathematics than physics. Beautiful but untestable. The honest truth is that we do not know which approach, if either, is correct. Loop, quantum gravity, and string theory are both incomplete. Both have technical problems that researchers are still working on, and both lack experimental evidence. This is the frustrating reality of trying to understand space-time at its deepest level. We are pushing against the limits of what science can currently test. But the quest continues, because solving this puzzle would answer some of the most profound questions we can ask about reality. Let us step back from these abstract theories and think about what space-time itself might be. Is it real? Is it physical? Or is it just a mathematical tool? Different physicists have different opinions. Some believe that space-time is as real as anything else. It is the stage on which physics happens. It curves, ripples, and expands. It interacts with matter and energy. In 2015, we detected gravitational waves. Ripples in space-time caused by two black holes colliding over 1 billion light-years away. The space-time fabric itself was stretched and squeezed as these waves passed through Earth. We measured this stretching with lasers. If that is not real, what is? Others argue that space-time is emergent. It is not fundamental. It arises from something else. Quantum entanglement, information, some deeper substrate that we have not yet discovered. In this view, asking what space-time really is might be like asking what temperature really is. Temperature is real in some sense. You can measure it. It affects how things behave. But it is not fundamental. It emerges from molecular motion. Space-time might be similar, real and useful, but not the bottom level of reality. There is even a more radical possibility. Some physicists wonder if space-time might be an illusion, a kind of user interface that our brains construct to make sense of reality. Evolution shaped our perceptions to help us survive, not to show us truth. Perhaps space and time are just the way our minds organize experience. The actual nature of reality might be nothing like the three-dimensional stage we perceive. These are deep philosophical questions, and physics alone might not be able to answer them. But what physics can do is keep testing, keep probing, keep looking for cracks in our current theories that might reveal what lies beneath. And right now, the biggest cracks are dark energy and quantum gravity. Solve these problems, and we might finally understand what space-time really is. But before we move on, there is one more aspect of space-time we need to explore: the weird and wonderful possibilities that general relativity permits. Because Einstein's equations allow for some truly bizarre structures that bend the mind as much as they bend space. We are talking about wormholes and time travel. A wormhole is a shortcut through space-time. Imagine folding a piece of paper so that two distant points touch. Then poke a hole through both layers. An ant walking along the paper could travel from one point to the other almost instantly by going through the hole. A wormhole works similarly. It connects two distant regions of space-time. You go in one end and come out the other, potentially very far away, or potentially very far in the past or future. Wormholes are valid solutions to Einstein's equations. They were discovered mathematically by Einstein himself, along with his colleague Nathan Rosen, in 1935. They are sometimes called Einstein-Rosen bridges, but there are serious problems with wormholes. The natural wormholes predicted by General Relativity are not traversable. They pinch off too quickly. Anything trying to pass through would be crushed. Or the wormhole would collapse before you could make it to the other side. To keep a wormhole open, you would need exotic matter. Matter with negative energy density. This sounds like science fiction, and in a sense, it is. We have never observed exotic matter, but quantum mechanics suggests it might exist in small amounts. Something called the Casimir effect creates tiny regions of negative energy between two metal plates. Whether this could be scaled up to stabilize a wormhole is unknown. Most physicists are skeptical. Traversable wormholes remain firmly in the realm of speculation. But wormholes open an even stranger door: time travel. If a wormhole could connect two different times, you could step in and emerge in the past or the future. You could meet your younger self, you could prevent your own birth. This creates logical paradoxes that have puzzled physicists and philosophers for decades. General relativity allows for another path to the past, something called a closed time-like curve. In normal space-time, your world line, the path you trace through four-dimensional space-time, always moves forward in time. Even if time slows down or speeds up, it always flows in one direction. But in certain extreme space-times, world lines can loop back on themselves. You could travel through space in such a way that you end up at the same time and place you started. You could meet yourself. Closed time-like curves appear in some solutions to Einstein's equations. One famous example is the Gödel universe, discovered by mathematician Kurt Gödel in 1949. Gödel was a friend of Einstein's, and his rotating universe model contained closed time-like curves throughout. You could travel to any point in your own past. Einstein found this deeply disturbing. 1. It suggested that time might not be what we think it is. The physicist Frank Tipler found another solution. An infinitely long, rapidly rotating cylinder could create closed time-like curves around it. Fly around the cylinder the right way, and you would travel back in time. Of course, we cannot build infinitely long cylinders, but the math works. Another possibility involves cosmic strings, hypothetical defects in space-time left over from the Big Bang. If two cosmic strings passed each other at high speed, they might create a region where time travel is possible. Again, we have never observed cosmic strings, but they are not ruled out. What about the paradoxes? What happens if you go back in time and prevent your own birth? This is called the grandfather paradox, and there are several possible resolutions. One is that time travel is simply impossible. The laws of physics might conspire to prevent any situation where paradoxes could occur. Stephen Hawking called this the chronology protection conjecture. The universe protects itself from paradoxes. Another resolution is multiple timelines. When you travel back in time, you do not enter your own past. You enter a parallel universe, a different timeline where events can unfold differently. In this view, you could prevent your grandfather from meeting your grandmother, but you would be preventing it in a different universe. Your original universe, where you were born, still exists unchanged. A third resolution is self-consistency. Perhaps anything you do in the past was always part of history. You cannot change the past because anything you try to change already happened with you trying to change it. If you go back to prevent an accident, your attempt was always part of the story. Either you fail, or the accident was not what you thought it was. History is self-consistent. There are no paradoxes because everything loops back on itself perfectly. These ideas push the boundaries of physics into philosophy. We have no experiments that can test time travel. We have no way to probe wormholes or closed time-like curves. But the fact that Einstein's equations permit these possibilities tells us something important. Space-time is stranger than we ever imagined, and our intuitions about space and time, developed over millions of years of evolution on a small planet, may not prepare us for the full truth. We have covered a lot of ground. We started before Einstein, with Newton's absolute space and universal time. We watched Einstein unify space and time into a single four-dimensional fabric. We saw how mass curves this fabric, creating the effect we call gravity. We explored black holes, where space-time curves so severely that nothing can escape. We learned about the expanding universe, driven faster and faster by the mysterious dark energy. We dove into quantum mechanics and saw why it clashes with general relativity, and we glimpsed speculative ideas about wormholes and time travel. But now it is time to confront the deepest questions head-on. What do we actually know about space-time? What remains mysterious? And why does understanding space-time matter so much? Here is what we know. Space-time is real. It can be measured. It curves around massive objects. We have photographed this curving with gravitational lensing. We have detected ripples in space-time with gravitational wave detectors. We rely on the warping of time for GPS satellites to work. Space-time is not just a mathematical abstraction. It is a physical thing that interacts with matter and energy. We also know that space-time is expanding. The universe is getting bigger, not because galaxies are flying through space, but because space itself is stretching. This expansion has been accelerating for billions of years, driven by dark energy. We know that space-time had a beginning. About 13.8 billion years ago, space and time emerged from an incredibly hot, dense state. What happened before that, or whether before even makes sense, we do not know. But we know that space-time has a history. It has evolved. It was different in the past and will be different in the future. Here is what we do not know. We do not know what space-time is made of. Is it continuous, like a smooth fabric? Or is it grainy like sand at the Planck scale? We cannot test this yet. The required measurements are far beyond our current technology. We do not know why space-time has the properties it does. Why 4 dimensions instead of 5 or 3 or 10? Why does it curve in response to mass? Why does it expand? These seem like questions that should have answers, but we do not have them. We do not know how space-time behaves at singularities. General relativity predicts infinite densities, but infinities are signs of breakdown. Something else must happen at black hole centers and at the Big Bang. We need quantum gravity to find out, and we do not have a complete theory yet. We do not know what dark energy is. We can measure its effects. We can parameterize it, but we cannot explain it. The vacuum energy calculation is off by 120 orders of magnitude. Something fundamental is missing from our understanding, and we do not know how space-time relates to consciousness. We experience time as flowing. We feel like we exist in a present moment that moves into the future. But physics describes a block universe where all times are equally real. Reconciling these pictures, the scientific and the experiential, remains a deep puzzle. Why does any of this matter? You might wonder why we should care about abstract questions about the nature of space and time. Here are some reasons. First, understanding space-time could lead to new technologies. General relativity gave us GPS. Quantum mechanics gave us computers and smartphones. A theory of quantum gravity might reveal new physics that we could harness in ways we cannot imagine. Perhaps new energy sources. Perhaps new ways to manipulate matter. Perhaps things we have not dreamed of yet. Second, understanding space-time helps us understand our place in the universe. We are creatures made of atoms, evolved on a small planet, in a vast cosmos. The space-time we inhabit shapes everything about our existence. Our sense of time, our experience of gravity, the fact that we can move through space. Knowing what space-time really is helps us know what we really are. Third, the quest itself has value. Human beings are curious creatures. We want to understand. We want to know. The mystery of space-time is one of the greatest puzzles ever posed. Solving it would be one of the greatest achievements of the human mind. Even if we never find a practical use for the answer, the search enriches us. Einstein gave us space-time over a century ago, and it transformed everything. It overthrew Newton. It explained gravity. It predicted black holes and gravitational waves and the expanding universe. But Einstein's gift came with questions attached, questions he could not answer, questions we still cannot answer. What is space-time? Is it fundamental or emergent? Is it continuous or discrete? What is the dark energy that fills it? How does it behave when gravity and quantum mechanics collide? These questions define the frontier of physics. They are the edge of human knowledge. And they remain open. There is something beautiful about this, something inspiring. We live in a universe that is still full of mystery. The very fabric of reality, the stage on which everything happens, the thing we are swimming in right now, remains deeply puzzling. Einstein showed us how much we can understand, but he also showed us how much remains to be learned. The next great breakthrough might come from a physicist working today. It might come from an experiment we have not built yet. It might come from a theoretical insight that connects ideas in a new way. Or it might not come for a long time. The universe is under no obligation to reveal its secrets on our schedule. But we keep asking, we keep probing, we keep searching. Because that is what humans do. Right now, you are moving through space-time. Every heartbeat carries you forward in time. Every step you take moves you through space. The atoms in your body curve the space-time around you ever so slightly. You are part of this fabric. You are woven into it. And though you may not understand what it is, you are experiencing it with every moment of your existence. Think about that for a second. You are made of space-time as much as you live in space-time. The atoms in your body were forged in stars. Those stars were born from clouds of gas that collapsed under their own gravity. That gravity was space-time curving in response to mass. Everything about you, your existence, your history, your possible futures, is written in the geometry of space-time. Einstein understood this deeply. He spent the last decades of his life trying to unify gravity with the other forces of nature. He did not succeed, but he never stopped trying. And he knew that the questions he raised would outlive him, that future generations would pick up where he left off, that the mystery of space-time would continue to inspire and challenge the greatest minds. And it has. Physicists today are still working on the puzzles Einstein posed. They have new tools, gravitational wave detectors, space telescopes, particle accelerators, quantum computers. They have new ideas, string theory, loop quantum gravity, emergent space-time. They are making progress. Slowly, painstakingly, they are chipping away at the mystery. But the mystery remains. And in some ways, that is the most exciting part. We are not done. The story of space-time is not complete. We are living in the middle of one of the great scientific adventures of all time. And we do not know how it ends. Maybe in 50 years, or 100 years, or 500 years, someone will figure it out. They will write an equation that explains what space-time really is. They will test it with experiments. They will prove it beyond doubt. And future generations will learn it in school, just as we learned Newton's laws, just as we learned Einstein's relativity. But right now, at this moment in history, space-time remains a mystery. The thing we know best and understand least. The fabric of our existence, the greatest puzzle ever posed. Einstein's idea that we still do not fully understand, and there is nowhere else any of us would rather be, at the edge of knowledge, staring into the unknown, wondering what space-time really is. Consider the simple act of lifting your hand. It seems like nothing special. You decide to move, and your hand rises. But think about what is actually happening. Your brain sends electrical signals down your nerves. These signals travel at a fraction of the speed of light, but they travel through space-time. The signals reach your muscle fibers, which contract. This contraction involves chemical reactions, atoms exchanging electrons, forces pushing and pulling, and every one of these interactions happens within the framework of space-time. The forces that move your muscles are electromagnetic. They are carried by photons, particles of light, that travel through space-time at the maximum possible speed. The protons and neutrons in your atoms are held together by the strong nuclear force, carried by gluons that zip around in space-time. The atoms themselves are mostly empty space, with electrons orbiting nuclei at distances determined by quantum mechanics and the structure of space-time. Even your sense of time passing, your feeling that there is a now, comes from processes in your brain. Neurons firing, memories forming, consciousness emerging from the dance of atoms and electrons. All of this happens in space-time. All of this is shaped by space-time. You cannot separate yourself from the fabric of the universe because you are made of that fabric. This is why the question of space-time matters so much. It is not just an abstract puzzle for physicists. It is a question about the nature of your own existence. What are you? Where are you? When are you? These questions lead inevitably to the question of space-time. And until we answer it, we cannot fully answer them. The ancient philosophers wondered about space and time. Plato asked whether space was a container that things exist in, or a relationship between things. Aristotle debated whether time was real, or just a measure of change. These questions were discussed for thousands of years. And then Einstein came along and showed that space and time are not separate, that they are woven together, that mass tells space-time how to curve, and space-time tells matter how to move. This was progress, huge progress, but it was not the end, because Einstein's equations, beautiful as they are, lead to singularities. They cannot explain dark energy. They clash with quantum mechanics. They leave us with as many questions as answers. Some people find this frustrating. They want final answers, complete explanations, a theory of everything that ties up all the loose ends. And that is a worthy goal. But there is also value in appreciating the journey, in recognizing how far we have come, in marveling at what we have learned even as we acknowledge what we have not. 100 years ago, we did not know the universe was expanding. We did not know black holes existed. We had not detected gravitational waves. We did not know about dark energy or dark matter. We had no theory of quantum mechanics. The progress of the last century is astonishing, and there is no reason to think progress will stop. The next 100 years might bring answers we cannot imagine, or they might bring new questions we cannot currently conceive. That is the nature of science. It is a journey without a known destination, a map that is always being redrawn, a story that is always being rewritten. And space-time is at the heart of that story. It is the setting of every event, the stage of every drama, the canvas on which everything is painted. Understanding it better will help us understand everything better. Because everything happens in space-time. Everything is made of space-time. Everything is space-time. Let us now go deeper into one of the most fascinating aspects of space-time, the way it behaves near extreme objects. We have touched on black holes, but there is so much more to explore. The physics near these objects reveals space-time at its strangest, and it gives us clues about what might lie beneath. Imagine falling into a black hole, not a tiny one that would rip you apart with tidal forces, a supermassive one, the kind that sits at the center of large galaxies, a black hole 1 billion times the mass of our sun. The tidal forces near its event horizon would be gentle enough that you could survive the crossing, at least for a while. As you fall, something strange happens to your perception. From the outside, an observer watching you would see you slow down. You would appear to freeze at the event horizon, never quite crossing it. Your image would grow dimmer and redder as light from your body struggles to escape the deepening gravity well. To the outside universe, you would be stuck forever at the edge of the black hole. But from your perspective, nothing special happens at the horizon. You fall right through. You do not notice any boundary. The event horizon is not a physical surface. It is just the point of no return, the moment when escape becomes impossible. You would not feel it. You would not see it. You would just keep falling. Inside the black hole, space-time is dramatically warped. Remember that outside a black hole, you can move freely in space, but you are forced to move forward in time. Inside the event horizon, this changes. The singularity is not a place in space. It is a moment in time, your future. No matter which way you point, no matter how hard you accelerate, you will hit the singularity. It is not ahead of you in space. It is ahead of you in time. Unavoidable, inescapable. This is one of the most mind-bending implications of general relativity. Inside a black hole, space and time switch roles in some sense. The singularity is a when, not a where. Your entire future lies in a single direction. And that direction leads to destruction. How long would you have? For a supermassive black hole, perhaps hours of subjective time. You could watch the universe outside, compressed and blue-shifted at the edges of your vision. Light from the outside would fall in with you, revealing the universe's future as you plunge to your doom. Some theorists have speculated about what you might see. The entire future history of the universe, compressed into your final moments. The death of stars, the evaporation of black holes, the heat death of everything, all witnessed in a flash before you hit the singularity. But what happens at the singularity? We do not know. General relativity says you would be crushed to infinite density. But infinite is not a physical quantity. It is a mathematical cry for help. Something else must happen. Perhaps quantum effects save you. Perhaps you pass through to another region of space-time. Perhaps reality itself breaks down in some fundamental way. Without a theory of quantum gravity, we cannot say. There is another prediction about black holes that has generated enormous interest in recent decades. Black holes are not entirely black. They glow. This was Stephen Hawking's great discovery in 1974. Using quantum mechanics near the event horizon, Hawking showed that black holes emit radiation. They have a temperature, and they slowly evaporate. This Hawking radiation comes from quantum effects at the boundary of the black hole. In quantum mechanics, empty space is never truly empty. Pairs of particles constantly pop into existence and then annihilate each other. Virtual particles, they are called. Normally, they appear and disappear so fast that they have no observable effect, but near an event horizon, something different can happen. A virtual pair can appear right at the edge. One particle falls in, the other escapes. The escaping particle carries energy away from the black hole. And since energy is mass, the black hole slowly shrinks. For a stellar mass black hole, this process is unimaginably slow. A black hole the mass of our Sun would take 10 to the 67th years to evaporate, far longer than the current age of the universe. But for very small black holes, evaporation is faster. A black hole the mass of a mountain would evaporate in about the age of the universe. And as black holes get smaller, they get hotter. They radiate faster. In their final moments, they explode in a burst of energy. Hawking radiation reveals a deep connection between gravity, quantum mechanics, and thermodynamics. Black holes have temperature and entropy. They obey laws similar to the laws of thermodynamics. This connection has led to profound insights about the nature of space-time. Some physicists believe that space-time itself might emerge from thermodynamics, that gravity might be an entropic force, arising from the statistical behavior of underlying quantum degrees of freedom. But Hawking radiation also creates a puzzle, the information paradox. When something falls into a black hole, information about what fell in seems to be lost. The black hole is characterized only by its mass, charge, and spin. Nothing else. A black hole made from a collapsed star looks identical to a black hole made from a collapsed cloud of books. The information about what went in appears to be destroyed. But quantum mechanics says information cannot be destroyed. It can be scrambled. It can be spread out, but it cannot be erased. So what happens to the information? Does it come out in the Hawking radiation, encrypted in some unreadable form? Does it stay inside, hidden in quantum correlations? Does it leak out through some unknown mechanism? This paradox has driven some of the deepest work in theoretical physics over the past few decades. It connects black hole physics, quantum information theory, and the foundations of quantum mechanics. And recently, there have been exciting developments. Using ideas from string theory and quantum information, physicists have argued that information does come out, very slowly, encoded in subtle correlations in the Hawking radiation. But the details are still being worked out. The information paradox shows how much we still have to learn about space-time. Black holes are not just exotic objects. They are laboratories for testing our deepest theories. They are places where gravity and quantum mechanics collide. And they are forcing us to rethink basic concepts like space, time, and information. Let us turn now to another frontier of space-time physics, gravitational waves. These are ripples in the fabric of space-time itself, propagating disturbances that stretch and squeeze space as they pass. Einstein predicted them in 1916, but it took exactly 100 years to detect them. When massive objects accelerate, they disturb space-time. Just as a boat creates waves on water, accelerating masses create waves in the space-time fabric. These waves travel at the speed of light, carrying energy and information across the cosmos. But they are incredibly weak. Even the most violent events in the universe create waves that stretch space by less than the width of a proton by the time they reach Earth. Detecting such tiny disturbances required extraordinary engineering. The LIGO experiment uses laser interferometry. 2 L-shaped detectors, one in Louisiana and one in Washington State. Each arm is 4 kilometers long. Lasers bounce back and forth along these arms, measuring the distance with exquisite precision. When a gravitational wave passes, it stretches one arm while squeezing the other. The interference pattern of the lasers shifts, and from this shift, we can reconstruct the wave. On September 14, 2015, LIGO detected its first gravitational wave. The signal came from 2 black holes spiraling together and merging, about 1.3 billion light-years away. Each black hole was about 30 times the mass of our Sun. They had been orbiting each other, getting closer and closer for millions of years. In the final fraction of a second, they merged in a violent collision that released more energy than all the stars in the observable universe combined. Most of that energy went into gravitational waves, ripples in space-time that expanded outward at the speed of light for over 1 billion years, until they washed over Earth and jiggled the LIGO mirrors by less than 1,000th of the width of a proton. This detection opened a new era in astronomy. We had always observed the universe with light. Now we can observe it with gravity. We can hear the cosmos as well as see it. Since 2015, LIGO and its partner detector Virgo have detected dozens of gravitational wave events, black hole mergers, neutron star collisions, events that produce no light at all, invisible to traditional telescopes but screaming in gravitational waves. One particularly exciting detection came in 2017. Two neutron stars spiraling together and colliding. This time, the event produced both gravitational waves and light. Telescopes around the world watched the aftermath. A burst of gamma rays, a glowing remnant that faded over days. The creation of heavy elements like gold and platinum, forged in the neutron star collision and flung into space. This was multi-messenger astronomy, observing the same event with multiple types of signals. It allowed scientists to learn far more than either signal alone could provide. We learned that gravitational waves travel at exactly the speed of light. We confirmed predictions about how neutron star collisions produce heavy elements. We tested general relativity in a new regime and found it still works perfectly. Gravitational waves are direct evidence that space-time is a dynamical entity. It can ripple and oscillate. It carries energy. It is not a passive backdrop, but an active participant in physics. When you feel gravity, you are feeling the shape of space-time. When gravitational waves pass, space-time itself is moving. Future gravitational wave detectors will push this frontier further. Space-based detectors like LISA will be sensitive to lower frequency waves. Waves from supermassive black hole mergers. Waves from the very early universe. Perhaps waves left over from the Big Bang itself, carrying information about the origin of space-time. Gravitational waves have also revived interest in some speculative ideas. If space-time has extra dimensions, gravitational waves might behave differently than light. They might take shortcuts through higher dimensions, or they might leak energy into dimensions we cannot see. By comparing gravitational wave arrival times with light arrival times, we can test these ideas. So far, there is no evidence for extra dimensions, but the search continues. Another connection involves quantum gravity. If space-time is granular at the Planck scale, gravitational waves might show slight distortions. High-frequency components might travel at slightly different speeds than low-frequency components. This dispersion would be a smoking gun for quantum space-time structure. Current detectors are not sensitive enough to see such effects, but future detectors might be. The detection of gravitational waves was one of the great scientific achievements of our time. It confirmed a century-old prediction. It opened a new window on the universe, and it reminded us that space-time is not just a stage. It is a character in the cosmic drama, a dynamic, flexible, responsive entity that interacts with everything it contains. Let us now return to one of our central mysteries, dark energy, the thing that is pushing the universe apart, the thing we cannot explain. The second great crisis of space-time, when astronomers discovered that the universe's expansion is accelerating, they were not sure what to call the cause. Dark energy is a placeholder name. It tells us almost nothing about what this substance actually is. We know it fills all of space uniformly. We know it has negative pressure. We know it is causing space itself to expand faster and faster. Beyond that, we are largely guessing. The simplest model is Einstein's cosmological constant, a fixed energy density inherent to empty space. Every cubic meter of vacuum contains the same amount of dark energy, no matter where or when. As the universe expands, new space is created, and that new space comes preloaded with dark energy. This keeps the energy density constant even as volume increases. It is as if the universe has an inflation setting that never turns off. The cosmological constant fits all current observations. It is simple, it is elegant, but it has that terrible problem. When we try to calculate its value from first principles, we get a number that is preposterously large. The predicted vacuum energy is 120 orders of magnitude greater than what we observe. If the vacuum had this much energy, the universe would have ripped itself apart immediately after the Big Bang. No stars, no galaxies, no planets, no us. So either our calculation is wrong, or something is cancelling most of the vacuum energy, leaving behind only a tiny residual. But what? We have no mechanism that would produce such precise cancellation. It would be like balancing a checkbook with 120 zeros and getting it right to the penny. This is the cosmological constant problem, and it is one of the most profound puzzles in physics. Some physicists have proposed that dark energy is not constant at all. It might be a dynamic field that changes over time. They call this quintessence. Perhaps in the early universe, the dark energy density was different. Perhaps it will change in the future. Quintessence models can fit observations, but they add complexity without solving the fundamental problem. Why is dark energy so weak? Another idea involves the anthropic principle. Perhaps the cosmological constant varies across different regions of the universe, or across different universes in a multiverse. Most values would be inhospitable to life. Too much dark energy, and matter would never clump into galaxies. Too little, and the universe might collapse back on itself. We find ourselves in a region with just the right amount, because only in such regions can observers exist to ask the question. This anthropic reasoning is controversial. Many physicists find it unsatisfying. It seems to explain nothing while explaining everything. It cannot be tested directly, and it abandons the dream of deriving the constants of nature from first principles. But in the absence of better explanations, some researchers take it seriously. Dark energy might also connect to modified gravity. Perhaps general relativity is not quite right at the larger scales. Perhaps gravity behaves differently across cosmic distances, mimicking the effect of dark energy. Various modified gravity theories have been proposed, but so far, all attempts to replace dark energy with modified gravity have run into problems. They either conflict with other observations or introduce worse fine-tuning than the cosmological constant. The truth is, we are stuck. Dark energy remains mysterious. It dominates the universe's energy budget. It determines the fate of the cosmos, and we cannot explain it. This is not a small gap in our knowledge. It is an enormous chasm. Understanding dark energy will require new physics. Perhaps the theory of quantum gravity will help. Perhaps new observations will give us clues. Perhaps a completely unexpected idea will crack the case. Whatever the answer turns out to be, it will likely revolutionize our understanding of space-time. Dark energy is not just a puzzle. It is a signal. Space-time is telling us that we have missed something fundamental, something hiding in plain sight, something woven into the very fabric of the universe. Now, let us consider the ultimate fate of space-time. If dark energy remains constant, the universe will expand forever. But not just expand. The expansion will accelerate. It will grow faster and faster without limit. What does this mean for the future? In the near term, cosmically speaking, not much changes. Over billions of years, distant galaxies will recede farther and farther. Eventually, they will be moving away faster than light. Not because they are traveling through space at light speed, but because space itself is stretching that fast. When this happens, light from those galaxies will never reach us again. They will slip beyond our cosmic horizon, lost forever. Our own galaxy will merge with Andromeda in about 4 billion years. The resulting megagalaxy will be an island in an increasingly empty universe. Other galaxies will fade from view. Future astronomers, if any exist, will see only darkness beyond their local group. They will have no evidence that the universe was ever filled with billions of galaxies. The expansion will have erased the evidence. Stars will burn out. The last red dwarfs will flicker and die in about 10 trillion years. The universe will go dark. Only stellar remnants will remain. White dwarfs slowly cooling. Neutron stars spinning down. Black holes drifting through the void. Over unimaginably long times, even these remnants will decay. Protons might be unstable, breaking apart over timescales of 10 to the 36th years or longer. If so, all ordinary matter will eventually dissolve into a thin soup of radiation. Black holes will evaporate via Hawking radiation, releasing their mass as photons that spread through ever-expanding space. Eventually, nothing will be left but a thin, cold gas of particles spread over a universe that is effectively infinite in size. The temperature will drop toward absolute zero. Nothing interesting will ever happen again. This is the heat death of the universe, the ultimate victory of entropy, the final state of space-time. But perhaps this is not the only possibility. If dark energy changes over time, the future could be different. If it grows stronger, the expansion could accelerate even faster. Space could eventually stretch so rapidly that even atoms are torn apart. This is called the Big Rip. Everything from galaxies to molecules to space-time itself would be shredded in a finite amount of time. Or if dark energy weakens or changes sign, the expansion could reverse. The universe could begin collapsing. Everything rushing back together. Temperatures rising. Density increasing. Eventually, another singularity. A big crunch. Perhaps followed by another big bang. An infinite cycle of expansion and contraction. A cosmic heartbeat that never stops. We do not know which fate awaits. It depends on the nature of dark energy, which we do not understand. But thinking about these possibilities reminds us how much is at stake. The question of space-time is not academic. It determines the ultimate destiny of everything. Of every galaxy, every star, every planet, every atom, of everything that exists or ever will exist. Let us now explore something that often gets overlooked when discussing space-time: the relationship between space-time and causality. Causality is the principle that effects follow their causes, that the future cannot influence the past, that there is a definite order to events. Space-time, as Einstein formulated it, has causality built in. The structure of space-time determines which events can influence which other events. In special relativity, there is a concept called the light cone. Imagine a point in space-time, a single event at a specific place and time. Now draw all the paths that light could travel from that point. In 2 dimensions of space plus 1 of time, this forms a cone shape. Everything inside the future light cone could potentially be affected by your event. Everything inside the past light cone could potentially have caused your event. Everything outside both cones is causally disconnected. No signal, no influence, no information can pass between your event and events outside the light cone. This structure protects causality. Since nothing can travel faster than light, cause and effect are always properly ordered. at least within special relativity, but general relativity allows space-time to curve, and severe curvature can create exotic causal structures. We have already discussed closed time-like curves paths through space-time that loop back to their starting point. If such paths exist, causality breaks down. You could influence your own past. The arrow of time would become a circle. Most physicists believe the universe does not allow such paradoxes. Stephen Hawking's chronology protection conjecture states that the laws of physics prevent the formation of closed time-like curves. Whenever you try to build a time machine, something goes wrong. Quantum effects destabilize the system. Energy requirements become infinite. The space-time configuration collapses before it can be used. But we cannot prove this conjecture. It is a guess, an educated guess, based on our intuition that paradoxes should not occur in nature. But until we have a complete theory of quantum gravity, we cannot be certain. The relationship between space-time and causality remains an open question. There is another subtle issue involving causality in quantum mechanics. Quantum entanglement allows two particles to be correlated in ways that seem to defy space and time. If you measure one particle, you instantly know something about the other, no matter how far away it is. This seems like faster than light communication, like one event is influencing another across space instantaneously. But it is not really faster than light signaling. You cannot use entanglement to send information. The correlations only become apparent when you compare measurements from both particles. And that comparison requires classical communication, which is limited to light speed. Still, entanglement reveals something strange about space-time. The correlations are non-local. They exist across space in a way that challenges our intuitions. Some physicists believe entanglement is a clue about the nature of space-time. There is a conjecture called ER equals EPR. ER refers to Einstein-Rosen bridges, also known as wormholes. EPR refers to the Einstein-Podolsky-Rosen paradox, the original thought experiment about entanglement. The conjecture suggests that every pair of entangled particles is connected by a tiny wormhole. That entanglement and space-time are deeply related. If true, this would be revolutionary. It would mean that the connectivity of space-time emerges from quantum entanglement. That space itself is stitched together by quantum correlations. Regions that are highly entangled would be close together in space. Regions with little entanglement would be far apart. Space-time would be a geometric representation of a web of quantum connections. This idea is still speculative, but it represents a trend in theoretical physics. The trend towards seeing space-time as emergent rather than fundamental. Instead of starting with space and time and adding matter and quantum mechanics, we might need to start with something else entirely, something more abstract, information perhaps, or quantum entanglement, or computational processes. And from this foundation, space-time would emerge as an approximate large-scale description. These ideas push against the boundaries of what we can currently test. But they are not just idle speculation. They are driven by real problems. The incompatibility of general relativity and quantum mechanics, the information paradox, the cosmological constant problem, the need for a theory of quantum gravity. Something is wrong or incomplete about our current picture. And fixing it might require rethinking space-time from the ground up. Let us now turn to the philosophical dimensions of space-time. Scientists often try to avoid philosophy. They want to focus on what can be measured and tested. But with space-time, the philosophical questions are unavoidable. They shape how we interpret the physics. They determine what we think the equations are actually telling us about reality. Consider the question of whether space-time is absolute or relational. Newton believed in absolute space and time, an infinite, empty container that exists independently of matter. Things move through this container. They occupy positions within it. The container would exist even if nothing were inside it. Leibniz disagreed. He argued that space is relational. It is defined by the arrangement of objects. If you removed all the objects, there would be nothing left. No empty container, just nothing. Space is the pattern of relationships between things, not a thing in itself. Einstein's general relativity seems to favor a version of the relational view. Space-time is dynamical. It is shaped by matter and energy. It curves in response to mass. In some sense, it is created by the objects within it. But this is not quite Leibniz's vision either. In general relativity, space-time can exist with nothing in it. A completely empty universe would still have space-time. It would just be flat. So space-time is not purely relational. It is its own kind of entity, interacting with matter, but not reducible to it. There is also the question of presentism versus eternalism. Presentism says that only the present moment is real. The past no longer exists. The future does not yet exist. We live in a constantly changing now, with a fixed past and an open future. This matches our everyday experience. We remember the past. We anticipate the future. But only the present feels real. Eternalism, by contrast, says that all times are equally real. The past still exists. The future already exists. We are not moving through time. We are spread out in time. Our lives are like worms extended through the 4 dimensions of space-time. What we call the present is just the point along this worm where our consciousness happens to be. General relativity strongly suggests eternalism. The block universe. All of space-time existing as a single, timeless whole. There is no universal now. Different observers disagree about which events are simultaneous. The very idea of the present moment becomes observer-dependent. If there were a universal objective present, it would pick out a preferred reference frame. And special relativity says no such frame exists. This is deeply unsettling to many people. It seems to conflict with our experience of time flowing, of the present being special, of the future being open, but perhaps our experience is misleading us. Perhaps the flow of time is an illusion created by our brains, a useful fiction that helps us navigate reality without being the full truth. Or perhaps there is something we are missing. Some aspect of physics or consciousness that rescues the idea of a moving present. Some physicists propose that quantum mechanics might provide this. The collapse of the wave function seems to happen at a moment. It seems to create a definite past out of fuzzy possibilities. Maybe this process is related to the flow of time, but this is speculative. We do not understand quantum collapse well enough to say, these philosophical questions are not just idle puzzles. They affect how we interpret the physics. They affect what we think quantum gravity is trying to tell us. They affect our entire worldview. And while physics alone cannot settle them, physics provides crucial input. It tells us what is consistent with observation and what is not. It narrows down the options. It forces us to confront possibilities we might otherwise dismiss. Now let us consider space-time in the context of the very early universe, the first moments after the Big Bang. This is where our theories are pushed to their limits, and where the mysteries of space-time are most acute. In the first tiny fraction of a second, the universe underwent a period of incredibly rapid expansion. This is called cosmic inflation. Space expanded faster than light. A region smaller than an atom grew to larger than a galaxy in less than a trillionth of a trillionth of a trillionth of a second. This sounds impossible, but remember, nothing is moving through space faster than light. Space itself is expanding, and there is no speed limit on that. Inflation was proposed to solve several puzzles about the observed universe. Why is the universe so flat? Why is the cosmic microwave background so uniform? Why do we not see certain exotic particles that Big Bang theory predicts? Inflation answers all these questions. It stretches space-time flat like pulling on a wrinkled balloon. It spreads any initial irregularities across cosmic distances. It dilutes the density of exotic particles until they are undetectable. But inflation raises its own puzzles. What caused it? What is the energy source that drove this expansion? The standard answer is a hypothetical field called the inflaton, a quantum field that filled the early universe with high energy density, pushing space apart. As inflation ended, the inflaton field decayed into ordinary particles. This reheating filled the universe with the hot plasma that would eventually become stars and galaxies. Inflation happened at energy scales far higher than we can probe with particle accelerators. We cannot test it directly. We can only look for indirect evidence in the cosmic microwave background, the leftover glow from the early universe. And that evidence is compelling, but not conclusive. The universe did something dramatic in its first moments. Inflation is our best guess for what, but we cannot be certain. What happened before inflation? This is where things get truly mysterious. The equations of general relativity break down as we approach the Big Bang singularity. The closer we get to time zero, the less we can trust our physics. At the Planck time, about 10 to the negative 43 seconds after whatever started it all, quantum gravitational effects should dominate. And we have no theory to describe them. Perhaps there was no before. Perhaps time began at the Big Bang or at the start of inflation. The question of what came before would be meaningless, like asking what is south of the South Pole. Perhaps the universe arose from nothing, some quantum fluctuation in a primordial void, a bubble of space-time that inflated from nothing into everything. Lawrence Krauss and others have explored this idea, but critics point out that the quantum vacuum is not really nothing. It is something. It has laws. It has properties. Where did those come from? Perhaps our universe is one of many, a single bubble in an infinite multiverse. Cosmic inflation might be eternal, constantly creating new bubble universes throughout an infinite space-time. Each bubble has its own Big Bang, its own inflation, its own physics. Our universe is just one among countless others. Perhaps the universe is cyclic, expanding, contracting, bouncing, and expanding again. An infinite sequence of cosmic cycles, no beginning, no end, just eternal repetition. Perhaps space-time emerged from something else entirely, some pre-geometric substrate that our current theories cannot describe, some mathematical structure or logical pattern that gives rise to space, time, matter, and everything else. We do not know. These are among the deepest questions humans can ask, and we are still far from answers. But the questions themselves are profound. They push us to the edges of knowledge. They inspire new ideas and new theories. They remind us that the universe is far stranger than our ancestors ever imagined. Let us now discuss some of the tools we use to study space-time. The experiments and observations that tell us what is real and what is not. Particle accelerators let us probe space-time at the smallest scales we can reach. By smashing particles together at high energies, we recreate conditions from the early universe. we see what matter does under extreme circumstances. The Large Hadron Collider at CERN has discovered the Higgs boson and confirmed key predictions of particle physics, but it hasn't yet found evidence of extra dimensions or quantum gravity. The energy scales where those effects become important are still far beyond our reach. Space telescopes let us probe spacetime at the larger scales. The James Webb Space Telescope is revealing galaxies from the early universe. Just a few 100 million years after the Big Bang, we can watch the cosmic web forming. We can see how structure emerged from the smooth early universe. And we can test whether general relativity works at these vast distances and early times. Cosmic microwave background observations tell us about spacetime when the universe was only 380,000 years old. This is when the universe cooled enough for atoms to form and light to travel freely. The patterns in this ancient light reveal the seeds of cosmic structure, tiny fluctuations that grew into galaxies. These patterns match the predictions of inflation remarkably well. They are our best evidence for what happened in the first moments. Gravitational wave detectors let us observe spacetime directly. When black holes merge, they ring spacetime like a bell. We hear these ringing vibrations with LIGO and Virgo. Future detectors, like LISA, will extend our hearing to new frequencies. We will listen to the entire gravitational wave spectrum, from the rumble of supermassive black hole mergers to the hum left over from the Big Bang itself. Precision atomic clocks test spacetime physics in our daily environment. They measure time dilation from Earth's rotation and from changes in altitude. They confirm that time passes at different rates at the top and bottom of a building. These effects are tiny but measurable, and they demonstrate that space-time physics is not just cosmic abstraction. It is happening right here, right now, all around us. These tools have taught us an enormous amount. They have confirmed predictions and revealed surprises. They have narrowed down the possibilities and opened new questions. And they continue to improve. Each generation of experiments is more sensitive than the last. Each pushes our knowledge a little further. We are still early in the journey of understanding space-time. But we are making progress. What would it mean to truly understand space-time? What would a complete theory look like? First, it would have to be mathematically consistent. No infinities, no internal contradictions. It would have to reduce to general relativity in the appropriate limit. When gravity is weak and distances are large, the new theory should give the same predictions as Einstein's equations. We know general relativity works in those regimes. Any new theory must match that success. Second, it would have to incorporate quantum mechanics. Gravity should be quantized. Spacetime should exhibit quantum behavior at very small scales. The theory should resolve the singularities that plague general relativity. It should tell us what happens at black hole centers and at the Big Bang. Third, it would have to explain dark energy. Not just accommodate it, but explain it. Derive the cosmological constant from first principles, or show why dark energy has some other origin. The 120 order of magnitude discrepancy between prediction and observation must be resolved. Fourth, it would have to make testable predictions, new phenomena we could look for, effects we could measure. Without testability, a theory is not physics. It is mathematics or philosophy. A true theory of space-time must put itself at risk of being wrong. Such a theory might also reveal deep connections between gravity and the other forces, between space-time and quantum information, between the mathematical structure of the equations and the physical reality they describe. It might unify all of physics into a single coherent framework. a theory of everything that explains not just spacetime, but all the particles and forces and constants of nature. Or it might not. Perhaps spacetime is not explained by a single elegant theory. Perhaps it is messy. Perhaps reality is complicated at its foundations. Perhaps there are brute facts that cannot be derived from anything deeper. We do not know. That is the honest answer. We have ideas. We have partial theories. We have tantalizing hints. But we do not have a complete understanding. Space-time remains a mystery. And yet, we have learned so much. A century ago, we did not know the universe was expanding. We did not know black holes existed. We had not thought carefully about space-time at all. Einstein's theories were brand new. Their implications were just beginning to be explored. Now we live in a universe revealed by those explorations. A universe of curved space-time and gravitational waves. Of black holes and neutron stars. Of an expanding cosmos accelerated by dark energy. Of quantum weirdness at the smallest scales and cosmic structure at the largest. We understand more than any generation before us. We see further. We know more, but the mystery endures. Space-time is not solved. It is not complete. The questions Einstein raised are still open, and they may be open for a long time to come. Let us consider some specific puzzles that illustrate just how strange space-time can be. These are thought experiments and physical scenarios that challenge our intuitions. They show that even after a century of study, space-time continues to surprise us. Consider the twin paradox. This is one of the most famous consequences of special relativity. Imagine two twins. One stays on Earth. The other rockets off to a distant star at nearly the speed of light, turns around and comes back. According to special relativity, time passes more slowly for the traveling twin. When they reunite, the traveler is younger than the stay-at-home twin. They have aged differently. This seems paradoxical at first. If motion is relative, should not each twin see the other as moving? Should not each think the other's time is running slow? The resolution is that the situation is not symmetric. The traveling twin accelerates. They change direction. They feel forces. The stay-at-home twin does not. This asymmetry breaks the apparent paradox. The traveling twin really does age less. We have tested this effect with precision. Atomic clocks flown on airplanes come back showing less time than clocks left on the ground. The effect is tiny at airplane speeds. But for hypothetical space travelers at near light speed, the effect would be dramatic. A round trip to a star 20 light years away might take only a year of ship time. But 40 years would pass on Earth. This is real time travel, not into the past, but into the future. By moving fast enough, you can skip ahead. Everyone you knew would age and die while you barely aged at all. This is not science fiction. It is confirmed physics. The fabric of space-time allows it. Consider also the length contraction of fast-moving objects. If a spaceship passes by at 90% the speed of light, it appears compressed, shortened in the direction of motion. A 100-meter ship would appear to be only about 44 meters long, not because of any optical illusion, because space itself has contracted for that moving object. From the perspective of people on the ship is its normal length, but the space outside has contracted. A journey of 10 light years becomes only about 4 light years. This is why time dilation and length contraction work together. The shorter distance at high speed takes less time to cross. Everything is consistent, but deeply strange. Consider the relativity of simultaneity. Events that are simultaneous for one observer may not be simultaneous for another. Imagine a train car with a light in the middle. The light flashes. Two detectors at the front and back of the car record the arrival of the light at the same time. For observers on the train, the two detection events are simultaneous. Now imagine an observer on the ground watching the train go by. From their perspective, the back of the train is moving toward where the flash occurred. The front is moving away. Light heading to the back has a shorter distance to travel. Light heading to the front has a longer distance, so the ground observer sees the back detector fire first. Bam! The events that were simultaneous on the train are not simultaneous from the ground. This is not just about perception or measurement delays. It is about the actual structure of space-time. There is no absolute fact about whether two events are simultaneous. It depends on how you are moving. This is why we cannot have a universal now. This is why the block universe picture is forced on us by the physics. Consider what happens at an event horizon. From far away, you watch something fall into a black hole. You see it slow down as it approaches the horizon. It gets dimmer and redder. Time dilation becomes extreme. The object appears to freeze at the edge, never quite crossing. From your perspective, it takes infinite time to cross the horizon. From the falling object's perspective, nothing special happens. It sails right through. It does not notice any boundary. The horizon is locally just ordinary space-time. The drama is all in the global structure. The fact that once inside, you cannot get out. But there is no sign, no barrier, no moment of crossing that you would notice. This creates interpretational puzzles. Is the infalling object inside the black hole or not? From far away, it never crosses. From its own perspective, it crosses immediately. Both descriptions are correct. They are different slices of the same four-dimensional reality. The block universe contains all of space-time, including the region inside the black hole that outside observers can never see. Consider the nature of gravitational potential energy. In Newtonian physics, gravitational potential energy is stored in the gravitational field. When you lift a ball, you put energy into the field. When you drop it, the field gives energy back. But in general relativity, there is no gravitational field. Gravity is space-time curvature. So where is the energy? This is actually a deep and unsolved problem. Energy in general relativity is hard to define. It is not localized in a clear way. You cannot point to a region of space-time and say how much gravitational energy is there. Different methods give different answers. This ambiguity has practical consequences for things like gravitational waves. They carry energy, but defining exactly how much and where is tricky. Consider the problem of time in quantum gravity. Quantum mechanics describes how things change over time. The Schrödinger equation tells us how quantum states evolve from moment to moment. But in general relativity, time is part of the fabric being curved. It is dynamical. It is not a fixed background against which things evolve. When we try to quantize gravity, we run into the problem of time. The equations seem to say that nothing changes, that the universe is static. This cannot be right. We obviously experience change. Time obviously passes. But finding where time comes from in quantum gravity is one of the hardest problems. Some approaches suggest time emerges from quantum correlations. Others suggest we need to radically rethink what time means. The problem remains unsolved. These puzzles are not failures of physics. They are signs that we are pushing into new territory. Whenever a theory reaches a frontier, paradoxes and confusions arise. They point the way forward. They show us where our understanding is incomplete. The puzzles of space-time are invitations to deeper discoveries. let us talk about the personal dimension of space-time. What does all this mean for you as a conscious being living your life? Every moment you experience is a point in space-time, a location in the four-dimensional fabric. Your life traces a world line through this fabric, a path from birth to death, winding through space and time. From the block universe perspective, your entire world line already exists. Every moment of your life is out there, frozen in the eternal structure of space-time. Does this mean you have no free will? Does it mean the future is fixed? Philosophers argue about this endlessly. Some say yes, eternalism implies determinism. If the future already exists, you cannot change it. Others say the block universe is compatible with free will. Your choices are part of the block. They are not made from outside and imposed on it. From within the flow of experience, you still deliberate and decide. The fact that these deliberations have eternal existence does not make them less real or less yours. I will not try to settle this debate, but I will note that the physics does not tell us what to believe about free will. It gives us a structure, space-time, within which events occur. How we interpret the experience of choice and agency is a further question. Physics constrains the options, but does not determine the answer. What physics does tell us is that your experience of time is tied to the structure of space-time. You remember the past because information flows from earlier events to later events along your world line. You do not remember the future because causation points in one direction. Entropy increases toward the future. Disorder grows. These asymmetries are built into the physics. They are why we experience time the way we do. Your sense of now, of a present moment that feels special, is harder to explain. Physics does not pick out any moment as privileged. All moments in the block universe are equally real. Yet you experience this moment as now. Not the moment you were born, not the moment you will die. This one. Why? Some physicists think this is an illusion. The present is just the moment where your consciousness happens to be. Every point along your world line feels like now to the you at that point. The sense of a moving present is a persistent illusion, created by the way memories work. Others think there might be more to it. That consciousness or observation plays a role in actualizing the present. That quantum mechanics somehow picks out a now. These ideas are speculative. They go beyond established physics. But they show that the question is taken seriously. Whatever the answer, your experience of space-time is real. The sunrise you watched this morning, the coffee you drank, the thoughts you are having now as you listen to these words, these are all events in space-time. They are as real as the sun and the moon and the distant galaxies. They are woven into the same fabric. You are made of atoms that were forged in stars. Those stars were shaped by gravity, which is space-time, curvature. The very matter of your body is a product of space-time physics, and your experience of that body, your consciousness, unfolds within space-time. You are not separate from the cosmos. You are part of it. A small, temporary pattern in the eternal fabric. This is humbling and awe-inspiring at once. You are tiny compared to the universe, a speck in the vastness of space and the immensity of time. And yet, you can understand space-time. You can grasp the equations. You can follow the logic. You can comprehend, at least partially, the fabric in which you exist. This is perhaps the most remarkable thing about humans. We are bits of the universe that have developed the ability to understand the universe. We are space-time contemplating itself. Matter and energy arranged in a pattern that asks questions and seeks answers. Whatever mysteries remain, this is already astonishing. Let us bring things together. We have traveled from Newton's absolute space to Einstein's curved space-time. We have explored black holes and gravitational waves, the expanding universe and dark energy. We have wrestled with quantum mechanics and the search for quantum gravity. We have pondered wormholes and time travel, causality and free will. We have seen what we know and acknowledged what we do not. What have we learned? First, space-time is real. It is not just a mathematical convenience. It is a physical thing that curves, ripples, and expands. It interacts with matter and energy. We can measure it. We can observe it. It is the arena in which everything happens. Second, space-time is not what it seems. It is not a fixed stage. It is a dynamic actor. It is not absolute but relative. It is not separate from time but unified with it. Our intuitions, built for life on a small planet at slow speeds, do not prepare us for its true nature. Third, space-time has mysteries we cannot yet solve. Singularities where physics breaks down. Dark energy we cannot explain. A clash between relativity and quantum mechanics. These are not minor gaps. They are gaping holes in our understanding. Filling them may take decades or centuries. Fourth, space-time connects to deep philosophical questions about the nature of time, about free will and determinism, about the relationship between physics and experience. These questions are not separate from science. They are woven into the interpretation of our best theories. Fifth, the quest to understand space-time is one of the great adventures of the human mind. It has already yielded enormous insights. It continues to inspire the brightest scientists, and it may eventually answer the most profound questions we can ask about reality. Einstein gave us the gift of space-time, a revolutionary concept that transformed physics and our picture of the universe. But the gift came with a challenge: to understand what space-time really is, to unify it with quantum mechanics, to explain its dark energy and its singularities, to comprehend the fabric in which we all exist. That challenge remains. 100 years after Einstein, space-time is still the deepest mystery in physics. We know more than he did. We see further than he could, but we still do not understand. And perhaps that is okay. Perhaps the mystery is part of the beauty. Perhaps the journey matters as much as the destination. We are alive at a moment when the greatest questions are still open, when the next breakthrough might be around the corner, when anyone with curiosity and dedication can contribute to the quest. Space-time surrounds you. It permeates you. Every atom in your body exists within it. Every thought you have unfolds through it. And despite a century of brilliant work, we still do not know what it truly is. That is not a failure. It is an invitation to wonder, to explore, to keep asking questions. The universe has given us space-time as a puzzle, the greatest puzzle ever posed. And we are still working on the solution. Right now, somewhere in the world, a physicist is scribbling equations on a whiteboard, trying to unify gravity and quantum mechanics, trying to explain dark energy, trying to understand black hole singularities. They are building on Einstein's work. They are extending human knowledge, and they are continuing the quest that began over 100 years ago. Maybe they will succeed. Maybe they will find the answer. Or maybe they will discover new questions we cannot yet imagine. That is how science works. Each generation stands on the shoulders of the last. Each pushes a little further into the unknown. You are part of this story. Even if you never write an equation or run an experiment, by wondering about space-time, you join the human project of understanding. By asking questions, you participate in the quest. By marveling at the mystery, you connect to something larger than yourself. The universe is vast and strange and beautiful, and space-time is its deepest secret, a secret we are still uncovering, a secret that may never be fully revealed. But the uncovering itself is the point. The wonder is the reward. Einstein once said that the most beautiful experience we can have is the mysterious. He spent his life exploring mysteries, and he left us with the greatest mystery of all. What is space-time? What is this fabric we call reality? What is the thing that contains everything and touches everything and shapes everything? We do not know, but we will keep asking, keep probing, keep wondering, because that is what humans do. That is what science is. And that is why, 100 years after Einstein, space-time remains the idea we still do not understand. There is one more aspect of space-time we should explore before we close: the way it connects to the deepest structures of mathematics. Einstein's equations are not arbitrary. They have a beautiful geometric form that reveals something profound about the relationship between physics and math. General Relativity is written in the language of differential geometry. This is the mathematics of curved spaces. It was developed in the 19th century by mathematicians like Gauss, Riemann, and others. They were not thinking about physics at all. They were exploring abstract questions about geometry. What kinds of surfaces can exist? How do you measure distance on a curved surface? What are the intrinsic properties of a space? When Einstein was struggling to extend special relativity to include gravity, he discovered that this mathematical framework was exactly what he needed. The universe is not flat, it is curved. And differential geometry is the language for describing curved spaces. Einstein learned this mathematics with help from his friend Marcel Grossmann. It took years of struggle, but eventually Einstein found the equations that describe how matter curves space-time. This is a remarkable fact. Mathematics developed purely for abstract reasons turned out to be the perfect language for describing physical reality. Einstein's equations are not just formulas that happen to work. They have deep mathematical meaning. They describe the geometry of the universe in the most elegant possible way. This raises a philosophical puzzle. Why is mathematics so effective at describing nature? The physicist Eugene Wigner called this the unreasonable effectiveness of mathematics. Why should abstract patterns invented by human minds match the structure of physical reality? Is math discovered or invented? Is the universe fundamentally mathematical? Some physicists and philosophers believe that mathematics is the deepest level of reality, that the universe is not just described by math, but is math. Space-time and particles and forces are all mathematical structures. We happen to be patterns within those structures, experiencing reality from the inside. This view, called mathematical universe hypothesis, is defended by physicist Max Tegmark among others. Others find this idea too extreme. They argue that mathematics is a human invention, a language we created to describe patterns. Its effectiveness comes from the fact that we developed it by studying nature. We built math to match reality, so of course it matches. These debates cannot be settled by experiment, but they remind us that space-time sits at the intersection of physics, mathematics, and philosophy. Understanding space-time is not just about equations. It is about the deepest questions we can ask about existence. Let us talk about some of the specific mathematical features of Einstein's equations. The central object in general relativity is called the metric tensor. It is a mathematical object that tells you how to measure distances in space-time. In flat space, the metric is simple. Distances are measured with the ordinary formula you learned in school. But in curved space-time, the metric becomes complicated. It varies from place to place. It encodes the curvature of spacetime at every point. Einstein's field equations relate the metric to the distribution of matter and energy. On one side of the equation is the Einstein tensor, which describes the curvature of spacetime. On the other side is the stress-energy tensor, which describes the matter and energy present. The equation says these two things are proportional. More matter and energy means more curvature. Less means less. This sounds simple, but the equation is incredibly difficult to solve. The metric appears on both sides. The equation is non-linear. Small changes can have large effects. Finding exact solutions requires special assumptions, symmetry, simplicity. Even then, the calculations are brutal. The simplest solution is flat space-time. No matter, no curvature, no gravity. Just empty space extending forever. This is called Minkowski space, after the mathematician who first described it. The next simplest solution describes spacetime around a single, spherical, non-rotating mass. This is the Schwarzschild solution, found by Karl Schwarzschild in 1916, just months after Einstein published his equations. Schwarzschild was serving on the Russian front in World War I. He solved the equations in the trenches. He died shortly after from a disease contracted in the war. His solution describes the spacetime around stars and planets. It predicts the bending of light and the precession of Mercury's orbit. It also predicts black holes, though. Schwarzschild did not realize this at the time. More complicated solutions describe rotating black holes, charged black holes, the expanding universe, gravitational waves, and more. Each solution reveals new aspects of spacetime. Each teaches us something about what the equations allow. But here is a key point. We do not know all the solutions. Einstein's equations are so complex that new solutions are still being found today, and we do not know if some of the solutions that exist on paper can actually occur in nature. The equations permit wormholes, but wormholes might require exotic matter that does not exist. The equations permit closed time-like curves, but chronology protection might prevent them. The map of possible spacetimes is still being drawn. This connects to another deep question. Why does the universe have the spacetime it has? Of all the possible solutions to Einstein's equations, why this one? Why this cosmology? Why this arrangement of matter and energy? Part of the answer is initial conditions. The Big Bang started with a particular state. That state evolved according to the equations. The universe we see is the result. But this just pushes the question back. Why those initial conditions? Another part involves selection effects. We can only observe a universe compatible with our existence. If the cosmological constant were much larger, galaxies would never form. If it were negative, the universe might have collapsed already. The fact that we are here constrains what kind of universe we can observe. But selection effects do not fully explain things. They tell us what range of parameters is compatible with life. They do not tell us why the parameters fall in that range. They do not explain dark energy. They do not explain the specific values of physical constants. Some physicists hope that a deeper theory will explain everything. A theory of quantum gravity that derives the initial conditions and the constants from first principles. A theory with no free parameters, where everything follows necessarily from the mathematics. Others doubt this is possible. They think some aspects of the universe might be contingent. Accidents of history, random outcomes of quantum processes, not derivable from any theory. We do not know which view is correct, but the question motivates research. It drives the search for deeper understanding. It is part of what makes space-time so fascinating. Let us return to the observational frontier. What are the big questions that current and future experiments might answer? One question is whether space-time is truly smooth or secretly granular. Loop quantum gravity predicts a minimum length. If space-time is granular, there might be observable effects. Gamma-ray bursts are being studied for signs that high-energy photons travel slightly differently than low-energy photons. So far, no dispersion has been seen. Space-time appears smooth down to the scales we can probe, but future observations might change this. Another question involves the nature of dark energy. Is it truly constant, or does it change over time? Surveys of distant galaxies are mapping the expansion history of the universe with increasing precision. The Dark Energy Survey, the Vera Rubin Observatory, and space missions like Euclid are collecting data that will constrain models of dark energy. If it varies, that would rule out a simple cosmological constant and point toward more exotic physics. A third question concerns the nature of black holes. Do they really have singularities at their centers? Does information truly escape via Hawking radiation? The Event Horizon Telescope has given us images of black hole shadows. Future observations might reveal subtle features that test our theories. Gravitational wave observations of black hole mergers give us data about what happens when two singularities collide. Each observation teaches us more about these extreme space-time objects. A fourth question is whether gravity is truly quantized. If gravitons exist, they should carry gravitational force the way photons carry electromagnetic force. Detecting individual gravitons is far beyond current technology. The effects are too weak, but indirect tests might be possible. If gravity is quantum, it should be able to create entanglement. Experiments are being designed to test this in laboratory settings. Success would confirm that space-time obeys quantum rules at some level. A fifth question involves the cosmic microwave background. The patterns in this ancient light encode information about the early universe. Inflation should have left specific signatures. Gravitational waves from inflation would create a particular pattern of polarization called B modes. Detecting these B modes would be strong evidence for inflation and would tell us about space-time at the highest energy scales. These questions drive current research. They motivate new experiments and observations. They push technology to its limits. And they might lead to breakthroughs that transform our understanding of space-time. Let us consider for a moment the human story behind this science. The people who have devoted their lives to understanding space-time. Einstein, of course, stands at the center. A genius who reimagined the universe. But he was not alone. Countless physicists, mathematicians, astronomers, and engineers have contributed. Some are famous, many are not. All have played a role in our collective understanding. Think of the graduate students running simulations at 3 in the morning. The engineers building gravitational wave detectors with impossible precision. The observers sitting at telescopes in remote mountaintops. The theorists filling blackboards with equations that might lead nowhere or might change everything. These people are driven by curiosity, by the desire to understand, by the sense that the universe has secrets worth uncovering. Science is a human endeavor. It is done by people with hopes and fears and limitations. It is messy and slow and full of wrong turns. But somehow, over time, it makes progress. We understand more now than we did a century ago. We will understand more in a century than we do now. This gradual accumulation of knowledge is one of humanity's greatest achievements, and space-time sits at the heart of it. The most fundamental subject in physics, the thing that underlies everything else. Understanding space-time is not just one problem among many. It is the problem solve it, and we unlock the deepest secrets of reality, fail, and we remain forever puzzled by the fabric of existence. We have come to the end of our journey together. We have traveled through space and time, from Newton's absolute stage to Einstein's curved fabric. We have visited black holes and gazed into singularities. We have ridden gravitational waves across the cosmos. We have wrestled with dark energy and quantum gravity. We have pondered the nature of time and the meaning of existence. What have we found? A universe stranger than we could have imagined. A space-time that bends and stretches and expands. A reality that defies our intuitions and rewards our curiosity. A mystery that deepens the more we learn. Einstein gave us space-time over a century ago. It was his greatest gift to humanity. A new way of seeing the universe. A framework that explained gravity and predicted black holes and gravitational waves. A vision that transformed physics and philosophy and our understanding of our place in the cosmos. But Einstein also gave us questions. Questions we still cannot answer. What is space-time made of? What happens where it breaks down? Why does it have the properties it has? What is the dark energy that fills it? How does it connect to the quantum world? These questions are our inheritance. They are the challenges Einstein left for future generations, and they remain open, waiting for the next breakthrough. The next Einstein. The next great leap forward. Maybe that breakthrough will come tomorrow. Maybe it will take centuries. The universe is patient. It has been hiding its secrets for billions of years. It can wait a little longer, but we cannot help asking, cannot help probing, cannot help wondering, because that is who we are. Curious creatures on a small planet, staring up at the stars, trying to understand the fabric of reality. Space-time is all around you. It is the stage on which your life unfolds, the medium through which light travels to your eyes, the reason your feet stay on the ground, the thing that makes the universe possible. And it remains after all this time, Einstein's idea that we still do not understand. Thank you for watching. If you made it this far, you are part of the quest. You have wondered about space-time. You have engaged with one of the deepest mysteries in science. And that matters. Every person who looks up at the stars and asks, why contributes something to our collective understanding? Every question asked brings us a tiny bit closer to answers. Keep wondering, keep asking, keep exploring. The universe is vast and strange and waiting to be understood. And space-time is the key to everything. Until next time, remember that you are a pattern in the fabric of space-time, a brief flicker of consciousness in the eternal block universe, a way for the cosmos to know itself. And that is perhaps the most remarkable thing of all. But before we truly close, let us take one more moment to appreciate the sheer strangeness of what we have learned. Think about what space-time actually implies about your daily experience. When you wake up in the morning, you are at a different point in space-time than when you went to sleep. You have traveled forward in time, carried by the relentless progression of your world line through the four-dimensional fabric. You have also moved through space, because Earth is spinning on its axis, orbiting the Sun, traveling with the Milky Way galaxy through the cosmos. Your position in space-time has changed dramatically, even though you lay still in bed. When you look at the Sun, you are seeing it as it was about 8 minutes ago. Light takes time to travel from the Sun to Earth. The Sun you see is slightly in the past. When you look at a distant star, you might be seeing it as it was hundreds or thousands of years ago. When you look at a distant galaxy, you are seeing it as it was millions or billions of years ago. Looking out into space is looking back in time. The sky is a time machine. When you feel the force of gravity holding you to Earth, you are feeling the curvature of space-time. The atoms in your body want to travel in straight lines through space-time. But those straight lines, in the curved geometry around Earth, curve toward the ground. What you feel as weight is actually the floor pushing up against you, preventing you from following your natural path through curved space-time. When you check your phone and use GPS to find your location, you are relying on corrections for both special and general relativistic effects. The satellites in orbit are moving fast relative to you, so their clocks tick slower due to time dilation. But they are also farther from Earth's mass, so their clocks tick faster due to weaker gravitational time dilation. The net effect is that satellite clocks run faster than ground clocks. Without accounting for this, GPS would be useless within hours. Every aspect of your daily life is touched by space-time. Every moment you experience occurs within its fabric. Every force you feel is a manifestation of its geometry. You are so immersed in space-time that you cannot notice it, like a fish that cannot notice water. But it is there. It is always there. And it is stranger than you ever knew. Consider also what space-time means for the nature of existence itself. In the block universe picture, all of time exists together. Your past self, taking your first steps as a toddler, still exists somewhere in the block. Your future self, breathing your last breath, already exists somewhere in the block. Every version of you, at every moment of your life, is equally real. This is hard to accept emotionally. We feel like the past is gone and the future is not yet here. We feel like we are moving through time, making choices that shape what will happen. But if the block universe is real, that feeling might be an illusion. A persistent, useful illusion, but an illusion nonetheless. Or maybe not. Maybe the block universe is too simple a picture. Maybe quantum mechanics introduces genuine indeterminacy. Maybe the future really is open. Maybe our choices really do matter in some deep ontological sense. These questions are still debated. The physics does not settle them definitively. What the physics does tell us is that space-time is not what we naively thought. It is not a fixed stage. It is not absolute. It is not separate from time. Our common sense picture of reality, developed through millions of years of evolution on a planet where speeds are slow and gravity is mild, does not capture the truth. The truth is stranger and more beautiful. Let us also consider what space-time might teach us about ourselves. As conscious beings embedded in space-time, we have a unique perspective on it. We experience time from the inside. We feel it flow. We remember the past and anticipate the future. We make plans and regret decisions. Our entire mental life is structured around time. But physics tells us that time is different from how we experience it. That all moments might be equally real. That the flow of time might be an illusion created by our brains. This creates a tension between science and experience, between what we know intellectually and what we feel viscerally. How do we resolve this tension? Some people ignore the science. They trust their experience and dismiss the physics as mere abstraction. But this seems wrong. The physics makes accurate predictions. It works. It describes something real about the world. Others embrace the science and try to reshape their experience. They meditate on the block universe. They try to feel the eternal now that physics describes. They seek liberation from the illusion of time's flow. This too seems difficult. Our brains are wired for the experience of temporal passage. We cannot simply switch it off. Perhaps the healthiest approach is to hold both perspectives lightly. To appreciate what science tells us about space-time, without demanding that our experience conform to it. To live in the moment while knowing that all moments might be equally real. To make plans for the future while understanding that the future might already exist. This is a kind of cognitive flexibility, a willingness to embrace paradox, an acceptance that reality might be stranger than our minds can fully grasp. And perhaps that is one of the gifts space-time gives us. Not just knowledge about the physical world, but humility about the limits of human understanding. We have barely scratched the surface. There is so much more to say about space-time. We could discuss the technical details of general relativity for hours. We could explore string theory and loop quantum gravity in depth. We could analyze the information, paradox, and the holographic principle. We could debate the philosophy of time and the nature of consciousness. But we have covered the essentials, the basic picture, the key insights, the central mysteries. You now know more about space-time than most people ever will. You understand that it curves around mass, that it expands with the universe, that it might be granular at small scales, that it breaks down at singularities, that dark energy fills it with unexplained force. You understand that Einstein gave us this picture over a century ago, that it has been confirmed by countless experiments, that it has revolutionized our understanding of the cosmos, and that it remains, despite all this success, fundamentally mysterious. What happens next depends on many things, on experimental breakthroughs, on theoretical insights, on the creativity of future scientists, on technologies not yet invented, on questions not yet asked. The story of space-time is not over. It is still being written, and you are now part of that story. Having engaged with these ideas, you carry them forward. You might discuss them with friends. You might think about them late at night. You might wonder about time and space in a new way. Every mind that engages with these questions adds something to the collective human understanding. Science is not just done in laboratories and observatories. It is done in minds, in conversations, in moments of wonder and confusion. Every time someone asks why time seems to flow, or what happens inside a black hole, or how gravity works, they are participating in the scientific quest. They are continuing the work that Einstein started. So keep asking, keep wondering, keep being amazed by the strangeness of space-time. The universe is under no obligation to make sense to us, but somehow, remarkably, it does. Partially, incompletely, with gaps and mysteries and paradoxes, but it makes enough sense that we can ask the questions, that we can make progress, that we can hope for deeper understanding. Space-time will continue to surprise us. It has surprises in store that we cannot imagine. Breakthroughs will come. Mysteries will deepen before they resolve. The next century of physics will be as revolutionary as the last, and space-time will be at the center of it all. We end where we began, with the simple fact that you are swimming in space-time right now, that every moment of your existence takes place within its fabric, that everything you see and feel and touch is a pattern in its geometry, that you are, quite literally, a piece of space-time that has learned to contemplate itself. What a strange and wonderful thing that is. What an unlikely and precious gift, to be here, to be aware, to wonder about the nature of the fabric that makes wondering possible. Einstein showed us what space-time can do. He showed us that it curves and stretches and bends. He showed us that it is not the static stage we once imagined, but a dynamic participant in the physics of the universe. But he also showed us how much we do not know, how deep the mysteries go, how far we still have to travel to understand the thing that surrounds and permeates everything. That is the legacy of space-time. knowledge and mystery intertwined, insight and wonder together, the thrill of understanding and the humility of ignorance. This is what it means to be human at this moment in history, to know so much and so little, to have come so far and have so far to go. To live in space-time while still struggling to understand what space-time actually is. May that struggle continue. May curiosity drive us forward. May wonder sustain us when the equations grow difficult and the experiments seem impossible. The universe has given us space-time as a puzzle. Let us keep working on the solution. And now, as this video ends and you return to your life, remember what you have learned. Space-time is not just physics. It is the fabric of your existence. It is the medium of your experience. It is the thing that makes everything possible. Carry that knowledge with you. Let it enrich your sense of the world. Let it remind you that reality is stranger and more beautiful than everyday experience suggests. And let it inspire you to keep asking the deepest questions, because that is what space-time invites us to do. To wonder, to question, to explore, to never stop seeking to understand the thing that contains us all. Einstein's idea that we still do not understand, the greatest mystery in all of science, the fabric of everything. There is a famous story about Einstein. Late in his life, when asked what he would do differently if he could live again, he said he would spend more time studying mathematics. He felt that the math was the key, that the equations held secrets he never fully unlocked. That deeper mathematical understanding would reveal deeper physical truths. This is characteristic of Einstein. Even after revolutionizing physics twice, with special and general relativity, he felt there was more to learn. He spent his final decade searching for a unified field theory, a single framework that would combine gravity with electromagnetism and explain all of physics. He never found it. But he never stopped looking. That spirit of relentless curiosity is what drives physics forward. Not satisfaction with what we know, but hunger for what we do not. Not comfort with our current understanding, but dissatisfaction that it remains incomplete. The greatest physicists are never done. They always see further mysteries on the horizon. Space-time embodies this spirit. It is a partial answer that raises deeper questions, a solution that creates new problems, a window that reveals how much more remains outside. Every insight about space-time leads to another mystery. Every answer generates more questions. This might sound frustrating, but it is actually beautiful. It means the quest never ends. It means there is always more to discover. It means science is not a finished cathedral, but an endless construction project. We are always building, always extending, always pushing the walls of knowledge outward. You are part of this construction project now. By learning about space-time, you have added another mind to the effort. By wondering about these mysteries, you have joined the ranks of those who seek to understand. You do not need to be a professional physicist. You do not need advanced degrees or laboratory access. You just need curiosity, and you have that. Otherwise, you would not have made it this far. The universe rewards curiosity. It reveals its secrets slowly, reluctantly, but it does reveal them. Every generation learns more than the last. Every decade brings new discoveries. The picture grows clearer over time, even as new puzzles emerge. Think about where we might be in another century. What will physicists in 2125 know about space-time that we do not? Perhaps they will have a complete theory of quantum gravity. Perhaps they will understand dark energy. Perhaps they will have detected gravitational waves from the Big Bang itself. Perhaps they will know whether space-time is continuous or discrete. That future depends on what we do now, on the experiments we build, on the students we train, on the questions we ask. The physicists of 2125 will stand on our shoulders, just as we stand on Einstein's. This is the great chain of understanding, each generation receiving knowledge from the past and adding to it for the future. Each person who wonders about space-time contributing something to the collective effort. The chain stretches back through Einstein to Newton and beyond, and it stretches forward to minds not yet born. You are a link in this chain. Your curiosity matters. Your engagement with these ideas is part of the ongoing human project to understand reality. Thank you for being here. Thank you for caring about space-time. The fabric of reality remains mysterious. But with curious minds engaged, there is hope the mystery will yield. The stars above you shine through space-time. The ground beneath you curves space-time. You exist, think, dream, and wonder within space-time. Now you know more about what that means. Not everything, but more than before. Keep asking questions. Keep looking up. The answer is space-time. And understanding space-time is the key to understanding everything.